We are wrapping up section 2 with two terms that get mixed up constantly, even by experienced engineers: sensitivity and resolution. People use them interchangeably, and that's a mistake that leads to a real problem when you are selecting instruments or interpreting measurements. By the end of this lesson, you will know exactly what each one means and, more importantly, why they are not the same thing. Let's start with sensitivity. Sensitivity is defined as the ratio of the change in output to the change in input. In plain language, it tells you how responsive the instrument is. How much does the output move when the input changes? Now, the easiest way to feel this intuitively is to think about car steering. Think about a race car. You make a tiny thumb of the wheel, just a small input, and the car responds with a large change in direction. That's high sensitivity. Small input, large output response. Now, think about a big truck. You turn the wheel a lot, a large input, and the direction barely changes. Small output response for a big input. That's a low sensitivity. So, high sensitivity means a smaller change in the input gives you a large change in the output. That's useful when you need to detect very small variations in the process. Low sensitivity means the output changes only slightly even for a large input change. Less reactive, but sometimes that's exactly what you want. In noisy environments or stable processes, a less sensitive instrument doesn't get rattled by every little disturbance. Let's put some numbers to this. Take a pressure transducer with a sensitivity of 2 millivolts per psi. That means for every 1 psi change in pressure, the output voltage changes by 2 millivolts. Now, compare that to a more sensitive version rated at 5 millivolt per psi. Same pressure change, but a bigger, stronger output signal. That stronger signal is easier to work with, especially over long cable runs where you might be fighting electrical noise. Now, look at the right side of the thermocouple example. A type K thermocouple has a sensitivity of approximately 41 microvolts per degree Celsius. 41 microvolts. That's a tiny signal. For every degree of temperature change, you are only getting 41 microvolts out of it. And this is exactly why thermocouple signals are so susceptible to electrical noise, and why they always require careful signal conditioning and amplification before you can do anything useful with them. The physics gives you a very small output per unit of input, so the signal to noise challenge is built in. Now, resolution. Resolution is the smallest change in the input that the instrument can detect and display. It's the finest step the instrument can report. Here is the analogy from the slide, and it's a good one. Think about a ruler. A ruler with millimeter marks has high resolution. You can see a 1 millimeter change. A ruler with only centimeter marks has low resolution. You can't see anything smaller than 1 centimeter. You are forced to estimate. Same idea applies to instruments. Take a digital thermometer with a resolution of 0.1 degrees Celsius. It can display 25.0 Celsius, then 25.1 Celsius, then 25.2 Celsius. Those are its steps, but if the true temperature is 25.05 Celsius or 25.06 Celsius. The thermometer can't show you that difference. It rounds to 25.1 Celsius for both. The step size is 0.1 Celsius, and anything smaller than that is invisible to the instrument. And there is a key quote on this slide that's worth reading out loud because it captures something really important. Resolution is the smallest step on the instrument scale. High resolution doesn't mean it's accurate. It just means it can show very small changes, even if those changes are wrong. That's the trap. An instrument with very fine resolution might display 25.001 Celsius with total confidence. But if it's not calibrated correctly, that precise looking number is precisely wrong. Resolution and accuracy are separate things. Now, let's put both concepts side by side, because this table is your reference, the kind thing worth coming back to. Definition first. Sensitivity is the ratio of a change in output to change in input. Resolution is the smallest detectable change in input that the instrument can display. Mathematically, sensitivity has a formula, delta output divided by delta input. Resolution doesn't have a formula in the same way. It depends on the scale divisions of an analog display or the number of digital steps in digital instrument. Their units are different too. Sensitivity is expressed in output units per input unit, milliamps per bar, microvolts per degree Celsius. Resolution is expressed in the same unit as the measured variable, just degrees, just bar, just volts, no ratio. The meaning. Sensitivity tells you how responsive the instrument is. Resolution tells you how fine the measurement steps are. From a technician's perspective, the question you ask yourself about sensitivity is the signal strong enough to be reliable over long wires and in a noisy environment? That's the practical concern. For resolution, the question is the instrument's display fine enough to see the level of detail I actually need for this application? Two different questions, two different specs, both need to be right. And the slide closes with two lines that I encourage you to memorize. Sensitivity equals slope. It's the strength of the instrument's reaction. But resolution equals step size. It's the fineness of what it can display. Slope and step size. That's your shorthand. That wraps up Lesson 8. And with it, Section 2 is complete. You now have a working understanding of all 5 core sensor performance characteristics: accuracy, repeatability, high stresses, drift, response time, and now sensitivity and resolution. In Section 3, we move into the documentation world: P&IDs, loop diagrams, instrument data sheets, and the standards that govern how everything gets specified and installed. See you there.